Welcome everybody. We are here in the rise of green threads. Here there is the QR of the full presentation if you need it to, I don't know, if you are in the last row and you don't see anything, you can download it right now. So let's start. Here we have a Xbox controller to change the slides. It's okay. So let's start with the history. Why did we need the concurrency? Basically, initially, we had only single core CPUs, and maybe we needed to use a browser at the same time of, I don't know, the mouse. So the concurrency was simulated because the user needed to view the UI of I don't know, Windows 95, and at the same time he needs to, I don't know, use the calculator, use the browser, and use multiple applications at the same time. So the history starts at 1991. Initially, the developer of the operating system thought that they needed a part of the operating system, basically in the kernel, to schedule multiple applications and decide which one needs to be executed at a certain time. For example, in 1991, we have the first release of Linux, which had a non-preemptive scheduler, and that means that the application itself need to do a system call or something that block its execution in order to pass the execution to another process. So there wasn't a fixed timer that if an application was lasting more than needed, terminated its execution. To see that, we needed to wait for Windows 95 in the 1995, which used predetermined limit of time for the execution of our application. Initially, the specifics of our computers weren't that great. For example, the first version of Linux ran on an CPU that used 16 megahertz, so it's like an Arduino, very low power, and it had 1 megabyte of RAM. Today we have something like 8 gigabytes or 16 gigabytes, so it's a huge difference. For Windows 95, the specs were a little bit higher. The CPU still was 16 megahertz. There were 4 megabytes of RAM, so not much, but at least the operating system supported these threads. So I don't know, something like a Java thread scheduled by the scheduler, by the way. The important thing to know is that they were one core CPU, single core CPU. So all the concurrency was simulated. We didn't have parallelism, so there weren't parallel core, but instead the execution was split in only one core. So here there is an image of example, and we see that the application 1 is the blue square, and the application 2 is the purple square. So it was kind of fake, but still handled by the OS kernel. So basically the coroutines were lightweight concurrency for weak CPU, and now we see that. What is a coroutine? Basically, a coroutine is a way to schedule multiple application threads inside the application itself. So the runtime of the application see that there are multiple threads. They are not OS threads, but the application starts a thread, and this thread, instead of relying on OS thread, is handled directly by the application runtime. And this was easy to handle because the CPUs were only single core CPUs. So they didn't need to handle concurrency or locks or optimize for multiple cores. It was kind of simple. We see that, for example, in Simula 67, created in 1967, so it was like 70 years ago, a lot of time. They created this first language with support for goroutines in Norway. And it was also the first OOP language, so a lot of time ago. But the support was very limited. There wasn't a runtime to handle them, but the single goroutine itself needed to throw the execution at the caller. So if there were multiple coroutines and one coroutine needed to stop after, I don't know, 10 milliseconds, the coroutine itself call a function in the language to signal that it needs to change the execution coroutine. Simula 67 was used for scientific computation. Was running on IBM mainframe, so a very huge computer with specs similar to the Windows 95 computers. So we have I don't know, some megabytes of RAM, single core CPUs, not much megahertz of computing power. And in the 1967, we are in the middle between COBOL and C. So for an historical point of view, this is the time in which we are, okay? So after COBOL, but before C. Another example of coroutine usage, at least the lightweight one, is the first version of Java 1.1, which is the first version with threads API. And why did they use green threads? Basically, we are in the context of single core CPUs. So I already said that we didn't need to optimize much. And in fact, they kept them only for 3 years because sometime later arrived the multi-core CPUs, and Java used only one OS threads to run all the coroutines. So they didn't handle the logs, etc. So when the 4-core CPUs arrived, they were like 4 times slower. Of course, they had only one OS thread, and the core of the CPU were 4. So here there is the source of Java documentation in which they claim that all the sources are underlined. So if you then want to download the presentation, you can see every one of them. So the Java Thread API basically after the 2000 wrapped completely an OS thread. Basically, they use it and wrapped it in an API to use it for the developer. So the developer wants to start a thread. He called the Java standard library, and Java standard library start an OS thread. And it is valid nowadays, of course. Okay, now we arrived in the modernity. Nowadays, computers. And now we see basically the Moore law, which in fact claims that every 1 year and a half, 2 years, the number of transistors doubles. So what is the number of transistors? It's not really direct correlation with the number of cores or the effective power, because in the CPU architecture world there are a lot of limitations. In fact, CPU builders like Intel or AMD found a lot of new ways to optimize the performance of their CPUs by not adding a lot of cores. In fact, nowadays we have a maximum of 16 cores in modern desktop CPUs. But they found a lot of ways, like hyperthreading, which is basically multiple two logical cores which share the CPU cache level 1, level 2. Or, for example, they added more cache because if we have more cache, we can optimize the performance of I don't know, code loading all the computation, because the CPU don't have to fetch the RAM, which is a much slower operation. So those are all the other techniques. You can fetch them yourself, but maybe another one is the specialized CPU instruction. For example, Intel added special instructions for vector calculation, which, for example, they are important for AI. Or they added also instruction for AES crypto computation. AES nowadays is everywhere in VPNs or literally everywhere. And they also added an internal risk score in, for example, x86. So Intel saw that CISC complex instruction set is hard to scale, so they translated the complex instructions to reduce the instruction like ARM internally in the CPU. So if you run an instruction that does multiple operations, internally Intel splits them in multiple small operations. So this is an example of a modern desktop CPU. We have 20 parallel threads. Here I use the hyperthreading feature as a simplification, but I just say 20. All the hardware, we don't care. So we have 16 gigabytes of RAM, which compared to 4 megabytes is 4,000 times more. So you can see the huge difference. And the frequency is 4 gigahertz, so compared to the 16 megahertz is 250 times, so still a lot. But the difference between computation and memory is significant. The drawing in the right is just an example of a modern OS scheduler. So like Windows 10, I took the image online, but basically we see that when threads enter it into an I/O operation, the scheduler put it in a queue, and the not running processes can be swapped into memory if the RAM is not enough. Classical computer awareness university course, by the way. So, what are threads? Basically, threads are a way inside a process to execute multiple flow of instruction in parallel. So they are handled by the OS scheduler, and for example, they are mapped to different cores, so they can run in the same moment. Or if there are more threads than the cores available, they are put in the queue and they just wait for the CPU free. So the second yellow drawing show that we can have multiple threads scheduled less cores. The time between the change of execution code is called context switch, which is not huge, but then we will see how much it takes. The last drawing in the left, we can see that a single process contains its code. We need to execute the code, of course, or it's not a process. The data, which contains the global variables, and the heap. So the heap is the part of memory that we just allocate dynamically, and the standard library take care of it, just allocate it. For example, when we use malloc or calloc in C. Then we have the registers, of course, the CPU registers, which are the current state of the execution, which we need them to, I don't know, add two variables, and we store two values into two registers and call the operation to add them. Then we have the program counter, which is the current instruction that we are executing, and it's increased by one if there is no branching, or if there is an if, maybe there is a jump to another instruction. And then we have the stack, which is the execution stack. So if we call a variable, the parameters are saved in the stack, and then the function is called. What are the threads? The threads are logically inside the process. They share all the code, all the data, and all the files. So these parts are static. They are the same for all the threads. But their difference is in the registers, in the stack, and in the counter, which is all the execution state of the code, of course. So multiple threads can run different instruction of the code. This part is clear until now. Raise your hands, please. Who didn't understand? No one. Okay, perfect. So in the right part, I have simplified the diagram using static allocation for the same threads, but this is not always true, because the threads can be scheduled in different cores. It's a choice of the scheduler. By the way, we have the main function of the application which is executed in the core 1 of the CPU. It calls a system call to create a new thread. Okay. So the example of the wrapped Java API, Java make a sys call to create this thread because the user code requested that. So the S, which is executed as a privileged instruction, so the pseudo permission, takes some time to create this thread because it needs to allocate the memory for the stack. It needs to do anything to add it to the queue. So this is called, and then return the response to the application call, which is the thread has been created. But at the same time, the thread has been created as a REST thread. So in this case, I assigned the core 2, which wasn't used before. And in this core 2, the thread execution starts, which can be any part of the code specified by the user in the thread creation, because the creation syscall contains what we need to start the execution with. Then I explained the context switch. Okay, so the context switch, what does? The context switch, first of all, saves all the state of the thread, so the registers, the stack, and the counter, and it saves in a part of memory, or maybe it was already in a dedicated part of memory, but it needs to be sure that it's saved for resume the execution later. Okay. Then load from memory the state of the other thread that needs to be executed, load into register, etc., and then restart the execution of the new thread. In the context switch, the scheduler can also say the thread that was running is still the most important one. So I don't save its state, and I just resume the execution without doing anything. This is a choice of the scheduler, okay? So, how much takes all these operations? Here, I made some calculation based on what I found online, and we do a context switch about 100 times in a second, so every 10, 15 milliseconds. And a single context switch takes 1000 nanoseconds, so it's 1 microsecond, which is, so in 1 millisecond there are 1000 of them, if you do that. So it's a little tiny amount of time. If we multiply the time of a single context switch for all the switches in a second, we see that every second we take 0.1 milliseconds for all the context switches. So it's a very insignificant amount of time, is 0.01%. So 99.91% is code execution, and 0.01 is this thread switch. So very tiny. And this is why threads are so widespread nowadays, because they enable the user to handle concurrency in a nice way, but they're not much performance angry. But still, we have some issue with threads. For example, we need a system call for every thread creation, and this can take also 1 second just for the creation, the location, and everything. So the initial stack is very high. In Linux, it's 10 megabytes, and if you need to find the RAM for 10 megabytes, it's not much for a single thread, but if you have a lot of threads, the memory can increase a lot. Okay, okay, the request is not 1 second, it's a millisecond, by the way. Sorry for the error. But it can take up to 10 milliseconds if we have to spawn like hundreds of different threads, because the operating system need to handle every request, and if there are a lot of them, of course, it will take much longer. Of course, with a large number of threads, the execution slows down, because we need a lot of memory, a lot of context switches handled by the scheduler. The scheduler handles everything, so it's an advantage for us, but we can't have much control on its operations. Basically, we can just assign a priority to the thread, and the scheduler handles everything. Yeah. So now we are in the era of internet. So we arrived in a moment where an HTTP server handles a lot of concurrent HTTP requests for multiple clients, and typically they are much I/O bound. So the CPU needs to wait a lot of time in internet packet send, receive the response and everything. But there isn't much computation to do. If you see a typical HTTP request, it's like read a file and return the result, or call a DB, or anything like that. So a lot of I/O, not much compute. But at the same time, we have 4 round trips for each HTTP request. One is for the TCP handshake, where we open the socket, and the server needs to respond to the TCP request. Then we have 2 round trips for the TLS exchange, so we are still at 3. And then there is the HTTP request, which is request and response, and this is another round trip. Well, one round trip is a request and response, okay? So if the round trip time, the the time between we send the request and we receive the response is very high. For example, if we are here in Italy and we call a server in US, the RTT time can be like 100 milliseconds. So if you need 4 round trips, the time to handle one request is half a second, something like that. So the big companies like Google and Cloudflare and Netflix need to spend a lot of more money if you use the normal threads because they have the disadvantage of be scheduled continuously, like they were designed for compute tasks. But at the same time, the internet usage has increased a lot. Like here I put a chart, and in the 90s was insignificant. Now we have 5 billion of users. And in this context, the coroutines plus, as I call them, arrives. So they started from 2010. Basically, they were initially introduced by Go, but maybe some other languages already started to see them. The idea is not anymore to use them as a lightweight concurrency for a single thread. But now their idea is to optimize them for modern CPU, take advantage of all the instructions. So they need to be ideal for I/O tasks, but also not much performance angry. So what are the characteristics of these new coroutines? They have an insignificant creation time, basically a fraction of millisecond. They are really, you don't see them. You can run also millions of them, and the runtime of the language still handles them correctly. Don't have much performance on the OS scheduler. And when a coroutine is blocked by an I/O task, the runtime separate them in another, another logical division, and the CPU can still run performance-wise threads. So since the I/O does nothing because it's blocked, you can still run other coroutines that need to be executed to calculate something, and you don't have this waste of CPU. So here I put a lot of names that I used by different languages to call them. For example, Java introduced them last year with the name of virtual threads. PHP initially had a library called AMPHP, but now they have fibers native in the language. Then we have Go with the goroutines, Python async.io use them internally. What are the characteristics of these languages? They are all backend languages. So this is because, of course, they are really great for I/O tasks like the rise of internet. And now, in the part 2, we will see the implementation of Go, not much code-wise, but more in a logical way, with also a bit of code. But before going on, I have some free stickers for you. I need one volunteer to distribute them, please. Yeah. So I have two kinds of stickers, the normal one and the one with sunglasses. You can get both of them. I printed them by myself, by the way. Okay. So, how many of you already used Go before? Only 3? Okay. So, I need one random guy that comes here. Come, come. Please. Yeah, I need one volunteer here. Because I have a gift for you. A plush.
That's so cool.
Yeah.
It's running in parallel.
Yeah, of course. No problem. Okay. So, what is Go? Go is a programming language born in 2009, and it has been created by real software engineers in Google, of course. Uh, of course, they organize free developer meetings like this one, but here we don't have much alcohol, unluckily. There isn't any. I hoped. You too, maybe. But it's focused on concurrency. So the goroutines are the central part of the language. And it's a very simple language to start into, but it's hard to really handle the concurrency properly. So maybe there are the channels, but someone that doesn't know anything about concurrency may do some errors, so it's important to grab the theory first. By the way, it's already 15 years old, so it's not born yesterday. And I chose that because its implementation of coroutines is one of the more mature around. They learned from their error, basically, over the years. And they redesigned their scheduler maybe more than one time to handle the maximum performance. By the way, the Go executable is compiled into a single file. So everything is statically linked. Every library is included in the binary. And that's why, because online you can see memes about, for example, hey, an hello world is 4 megabytes, that's crazy. Of course, everything is statically compiled. For example, in C, the standard library is in a separated dynamically linked OS library. So when the code executes, the call like printf or the call to open a file are forwarded to this statically linked library. I made a joke about Temple OS, by the way. But in Go, every syscall is handled by the runtime, which is a part of the compiled binary that handles all the execution. In C, instead, we make a call to the external library, and the library make the syscall to the operating system, and then gets a response and handles everything. So don't be scared, but this is actually assembly. So I will explain that. So here I chose to take a part of Go to show you that the Go language is optimized for modern CPUs, like I explained before. Here I chose the map-hash implementation, so the key calculation for an hash map, basically. In the first picture, we see that everything starts in the map-hash package, which is part of the Go standard library. And this map-hash called an RThash function to calculate the hash, of course, in both in the insert and in the retrieval, because when we insert, we need to calculate the hash to put it into a bucket. But when we retrieve it, we need to calculate the key and retrieve the data, by the way. Then, of course, we finish into assembly which you must love it, of course. What we do in assembly? Basically, if the AES instructions are available, they calculate a non-cryptographic hash using the AES instructions. And this is very clever because the fallback is another function called yhash. And the difference is like 3 times lower, so they really optimize it. And of course, the fallback is just yhash. And then we can know at compile time if the running CPU has these instructions, because the executable need to run everywhere. So instead of just not optimize them, they initialize a Boolean variable at startup to know if the instructions are available. And in the assembly, we check the Boolean variable, and if it's true, they use the AES instructions. So the initialization is slightly slower, but the performance increase is really higher, as you can see. So the initial stage of Go. Initially, the Go compiler was just written in C. So, of course, every language needs to start with a base. C was written in assembly initially. It was a Google project. Of course, initially, they didn't have that much budget to hire hundreds of engineers. They just needed to start, present their idea to the company. So initially, I'm talking about the period between 2009 and 2014. It wasn't super ugly optimized. Basically, no one used it. It was an entire project, proof of concept, like. Over the time, the language changed. In 2015, the Go team completely redesigned the scheduler from scratch. Anyway, we'll see it later. And in 2020, so like 4 years ago, not much time ago, they added the possibility to have it fully preemptive, because before 2020, the goroutine itself needed to pass the control because it was cooperative scheduling. Yeah. So it was like Linux 0.01. Okay. So what is the scheduler? This is an example drawing. Like your scheduler is a shovel that assigns the threads to the CPU and decide which thread need to run in which moment. Now, if we use the goroutines, we have 2 schedulers. The OS scheduler, which of course handles the OS threads, and the Go scheduler, which assigns the goroutines to the threads. So the goroutines are not directly executed as a replacement for threads, but they are an abstraction over threads to run the I/O task better with a lower memory consumption. For example, the initial memory usage for a goroutine is like 1 kilobyte, 2 kilobytes, compared to 10 megabytes of a thread. And this memory, stack memory, of course, can grow if needed. So it's not a fixed size. So in Go, there is this Go max pros environment variable that set the limit of concurrently running threads. If the Go max pros value is 4, we can have 4 threads at the same time, and the goroutines can be 1,000, and those 1,000 goroutines can run in these 4 threads. Oh, of course, we can manually set it, but by default is the number of CPU cores to have the maximum performance available. Of course, the Go scheduler is part of the runtime, which we have seen before. It also handles the context switch of goroutines, which, by the way, are much faster than a thread context switch, like 20 times lower, 15 nanoseconds. Of course, the threads are scheduled independently by the OS scheduler. Go doesn't touch them. They just create the threads and use them. So the basic of everything in goroutine scheduling is the PMG model. So what is the PMG model? Basically, the developer team thought about a way to maximize the CPU performance in their implementation. So in this model, the G represents a goroutine, the coroutine basically. M means machine, and it's a CPU thread, and P is a process, which is a logical concept. So it doesn't correspond to a real OS thread, but it's just a limitation for the running threads. So these, for example, the procs. Procs means processors. Okay. So in the environment variable, go max proc means go max processors. So the initial stack is 2 kilobytes, 5,000 times lower. The OS thread, which is the machine, has its own stack to run the runtime. So when a goroutine finishes the execution, the runtime needs to schedule another goroutine, and the scheduler runs the CPU. So we need the stack to know which routines we need to run. And here I have a drawing with a dual-core CPU. We can see that there are 3 threads, but the Go max process here is 2. So why this? Because in the meanwhile, one of the threads is blocked in a syscall. So if we, for example, if we open a file, the syscall is synchronous. So the whole thread is blocked. So initially, we had just, I don't know, G0 was in M0, but G1 was in M0, was assigned to M0. But the G1, the G0 routine called the syscall blocked the OS thread. So what did Go do? Go removed the thread M0 from the process that it had, and it separated the routine that was running into it in another part, or logical part at least. So Go created another thread, in this case called M1, to run the remaining goroutines that weren't affected by the blocking syscall. So in this case, we're creating a new thread to maximize the performance of the concurrent running threads. Okay. And this needs to be clear because it's fundamental in the PMG model. So here I have an example, a complete example of an execution. Initially, all the processors were idle. We didn't have any task to do. They just were in a queue, free to be taken. Then we run the main routine, which needs, of course, its own OS thread. So the OS thread M0 is created. The processor is free, so it immediately assigns the available computation. But the goroutine decided to spawn another goroutine. In this case, I call it G1. So processors are free, another thread is created, and in the little queue, we still have 2 processors available. Then G1 call a blocking syscall, so maybe it opens a file. So what happens? The processor assigned to the G1 is free because G1 is blocked. So the other queue now has 3 elements. Why 3 elements? Of course, because before we have 2, and now we have one more process free for computation. So if there were other goroutines, the processing power could be assigned to other goroutines. Now, G1 finished the blocking syscall. What happens? First of all, we try to acquire the same processor if it's still in the idle queue, of course, because if you try to do that, we have the cache advantage, we still have the data ready in the caches, so the execution will be more performant. But if it's already assigned, we try with another casual P in the idle list. So in this case, we take M1 and we assign it to any available P. We assign the whole thread because now the thread is not blocked anymore. We can freely assign it. But if this is not available, we just put the now available thread in another queue called idle thread queue. So if in the future a new thread is needed, it just can be taken from this queue, and we don't have to create a new one because this one is already idle. And the coroutine is assigned to a global run queue, which we'll see in a moment. And this global run queue basically is a queue of goroutines ready to be executed. Okay. The run queues. So we have the global run queue, which is a shared queue within all the Ps. And then we have one local run queue for every P. So for every processor, we have a local queue of goroutines assigned to that process. So if one routine, in this case G1, blocks the thread is removed from the process, but the local run queue still belongs to the process. So we can create another thread or take it from the idle thread list and just execute another routine. And the local run queue is important also for the caches, because if we run a restricted number of routines for each CPU core, we just optimize the caches, of course. Okay. Yeah, of course, we don't have only one global queue for that, but also because in this way we reduce the competition of each thread to take a task, because if we have a local run queue, the queue is only of the running thread, so it doesn't have to lock a mutex or something like that. Another important part is the work stealing feature, in which basically if one thread finishes the local run queue and has nothing to do, it just steals a task from another local run queue and it executes it instead of just doing anything, because it's free. Needs to execute. This is basically the context switch of the goroutine. They have implemented it in a function called find runnable in runtime. How does a context switch work in Go? Basically, first of all, the Go scheduler check if there is a garbage collection goroutine to run. So if there is, it just runs a garbage collection. Isn't there a garbage collection? One time over 61, it takes any task from the global queue if present. So why 61? I don't know. Here I posted the code, and you can see they just put module 61, and they said it's for fairness. Okay, well, we believe them. Yeah. So of course, this is done because if the goroutines in the local run queue continuously execute, the new threads, the new goroutines to execute in the global run queue can be executed because there is starvation from the local run queue. So in the other 60 times, we just check in the local run queue if there are threads, if there are goroutines. If there are goroutines in the local run queue, just execute them. Then we check the global run queue. So in this case, we finish the execution of a goroutine. In our local run queue, there is nothing to execute. We check in the global run queue if there is something that is waiting, basically. If even in this case there is nothing, we just poll the kernel. So, for example, in Linux there is a system call called epoll to check if there is any network data received, and if yes, we check our goroutines to see if the goroutines received the data. In this case, the goroutines that are waiting for the netpoller are in a separated queue. Here, for example, this is G4. So it's an asynchronous task. In this way, if we, for example, run an HTTP call, we are not in a blocking call. So we are not blocking the whole thread like a file reading. But instead, we are moving the goroutine to the netpoller, and we can run in the same thread. In this case, I don't know, G4 was running M2, for example. In the same thread, we can run other goroutines in the local run queue, global run queue, etc. So if the netpoller finds the data and a goroutine can now be resumed, it just run it. If not, it just steal a task from another local run queue, and if there is no task, there is nothing to do, nothing to do, so it just wait and restart the cycle, basically. Okay. Okay, so in a preemptive scheduling, of course, the execution of a certain routine can stop for IO, syscall, etc., or for the assigned preemption time, which is finished. So in Go, the slot is 10 milliseconds. So after 10 milliseconds, there is a part of the go runtime, which is a separated thread not counted in the active thread, so it doesn't influence the procs value. This separated thread sends a signal to the threads, to the thread running the goroutine, and these signals pass the control of the thread to the go runtime, and the go runtime processes the context switch because the goroutine is taking too much time. Of course, classical context switch, it dumps the state, execute another goroutine, or maybe the same one if there isn't any other. So we arrived at the benchmark part. Here we just check if the goroutines are more performant than normal threads. And now you say me, but in Go there are no threads. How you're doing that? If you compare using different languages, it's impossible because it doesn't make sense since they are two different languages. And here I use a trick called localhost thread, which is a function of the standard library that statically assigned the thread to the goroutine. So in the PMG model, it's something like MG0. They are one only thing. When the execution finishes, the thread is always deleted because I never call the unlock_OS thread. So this way, it's a kind of trick to run a full OS thread. I use this in my benchmarks against the normal goroutines. So let's see. Initially, I tried with a CPU bound task because I wanted to see the difference in performance. So for my benchmark, all the code is in a GitHub repository linked here. Linked here in the GitHub repository. Here, I want to run multiple rounds of SHA 256 on random data, and I tried that in different threads or goroutines to see the difference. So I tried with different values of n. I tried 8 threads and goroutines, 32 and 100, but I didn't see any significant difference between them. Of course, every value that I measured is the average between 5 different mesurations, so there can be any outlier or better. There can be some outliers, but in the average, it's not much significant. So I tried with different values of k, so the number of SHA 256 rounds, and k I used any value between 10 and 100,000. So 100,000 rounds of SHA is takes something like 1 second or something like that. For lower values of key, I saw that the goroutines beat threads by 10-15%, and that's why, because their startup time is much lower. But for the maximum value of key, the difference is insignificant. So maybe in my head, the thread on the long term was more performant, but I need a way to test that. But of course, we can conclude that threads are not ideal if we need to continuously spawn them, because of course, the startup time is higher. So I need another test where I start the benchmark after the spawn of threads. So before I spawn all the threads or goroutines based on the test, and I pass the task using a channel, so basically something like a notification, and then the threads sends in another channel that it finished the execution, and we restart our benchmark. Okay. So in this second benchmark, I saw that in my laptop, if the number n of threads is equal or less than the number of physical cores, the threads are more performant, like 10-50%. So it's reversed. And the lower the threads, the more the difference was. But if n, so the number of concurrent threads is higher than the available cores, the coroutines beat basically the threads. Maybe because the scheduler is better. I didn't test it, but it's my conclusion. So here, I didn't report the result because I didn't have time, but you can write it yourself using the GitHub repo. Okay, so our conclusion is, should I use a locked thread instead of a goroutine? No, because it's not a standard in the language. Basically, the language is built around goroutines, and the performance gain is 10%, so not much. and it decreases if the number of threads increases. So I still use the goroutines, but there are some cases where the Go thread, so the locked locked thread is needed. So, for example, last week I did a task with XDP, which is a high performance networking that bypasses the Linux net stack. So very low level stuff. And in this case, I needed to lock the thread because the state of the thread was modified, and I needed more performance basically. So in this restricted case, they can be useful. And Go also create the locus thread because they use it also in their runtime for when they need to modify the thread state. So now I want to test it in IO task. So in this case, I started a hello world server. So basically, when we do a request, every response is hello world. We don't care about the path, about anything. The server just responds hello world to every request. And in this case, first of all, I run the server in another process to not influence the scheduler performance, because if we have two processes, the runtimes are independent from each other. And in the clients, I created an HTTP client for each request. So there was stuff like keep alive, so caches or anything like that that could influence the benchmark. And in this created client, I just run one request and then throw it away. Okay. For the benchmark task, I increased the GoMaxPros to the value. Like if we had 32 threads, I set it to 33 to have the main routine plus the 32 threads. So we can run every thread at the same time if needed. So those are the results of the benchmark. Every measure is the average of other measures. So for 4 threads of routines, the difference is 25%. So the coroutines are 25% faster, but we reach 100% with 2,000 requests. So it's basically the double. So if you use the threads, we lose half of the performance in IO task. And wow, the double is not insignificant. So why didn't I do a benchmark like before, where I spawned all the threads, all the routines, and just use them continuously? Well, because in IO tasks it's not feasible. If we know, we can run something called thread pool, where we store continuously running threads or routines. But in this case, the IO task is not predictable. Maybe we need to make more requests in one time, and later there are less. So in this case, we will need to spawn the required threads. But if they were lower than the number we needed, we would have to wait, basically. Because if we have to do 32 requests and we have 16 threads in the pool, we take double the time. So this wouldn't be a realistic benchmark if we spawned all the threads before, because we can know the traffic spikes or everything like that. But of course, with something like DB connections, which are persistent, we can just have them. In fact, all the Go libraries for Postgres, for example, use persistent DB connections in a pool, and you want to have them because you can run authenticated connection for every query. It would be crazy. Okay, we reached the Q&A. This is the link to download the slides, and if you have any questions, you're not much now. But